In this video here, we're going to take a look at oblique impact of smooth spheres. Now we can solve problems involving the oblique impact of two smooth spheres. Now the methods that we use to solve problems involving the impact between a sphere and a fixed surface can be adapted here to solve problems involving the impact of two spheres. Now, at the moment of impact, the two spheres have a common tangent which is perpendicular to the line through the centers of the two spheres. And hopefully the diagram below here will help illustrate this concept. So there's a few key points here to make right regarding this concept and this diagram here. So for the first point then, just note here that the reaction between the two spheres acts along the line of centers. So this dashed line here through the center of each sphere. And in that case, then the impulse here affecting each sphere also acts along the line of centers again, as this dashed line here. Now for the second point then, the components of the velocities of the spheres perpendicular to the line of centers are unchanged in the impact. For the third point here, Newton's law of restitution applies to the components of the velocities of the spheres parallel to the line of centers. And for the very last point here, the principle of conservation of momentum applies parallel to the line of centers. So again, a few different points to take in here, but please do make a note of these points here. These are really, really important, okay? And we'll see a demonstration of this as we work through a practice question very shortly. And to finish with here then, the principle of conservation of momentum also applies perpendicular to the line of centers. However, as the components of velocity in this direction are unchanged, you will not need to use these in your calculations, okay? So not something that you do need to worry about. So in terms of an introduction here then to oblique impact of smooth spheres, as I said, right, there's a few different key points here that you do need to be aware of. I can't speak anymore, but you do need to be aware of these key points here, right? So please do make a note of these here before we work through the practice question, okay? So there we have it then. That concludes this introduction here to oblique impact of smooth spheres. As always, I think the best way to really demonstrate this here is just work through a practice question. So let's just get started then with this practice question here. All right, so let's just get started then with the one practice question here for oblique impact of smooth spheres. Now for this question, then what we've got here is a smooth sphere A of mass 3 kg that's moving with this speed here, so 10 meters per second. Now it collides obliquely with a smooth sphere B of mass 2 kg, and just before the impact B is stationary, and the velocity of A makes an angle of 60 degrees with the lines of centers of the two spheres. The coefficient of restitution between the spheres is 1/2. So for this question then, all we want to do here is just find the magnitudes and the directions of the velocities of A and B immediately after the impact. Now the first problem here, and hopefully it's quite obvious, is that we don't have a diagram. So trying to solve this problem here, this question, without a diagram is asking for trouble. So don't be lazy then, just draw a diagram, right? And for this question here, I actually require two diagrams. So for the first diagram here, this is for before the impact. And then for the second diagram here, which we'll draw in just a moment, that's for after the impact, okay? So starting off then with the before diagram, well, clearly we need two spheres here. And it doesn't need to be a mass piece, by the way. So that is sphere A there. And we also have sphere B, something like this, right? And through the center then of these two spheres here, look, my center there and my center, let's just say there, right? We have the lines of centers, something like this. Clearly it should just be a straight line. But like I said, I'm no artist, but it'll do for now, right? So what else do we know here? So we know that this sphere here, and I said particle, this sphere here has a mass of 3 kg. So 3 kg. And then this sphere here has a mass of 2 kg, as the question tells us. So 2 kg. What else do we know here? So I'll do this in a different color. So what we also know here is that sphere A is moving with a speed of 10 meters per second, and it collides and makes an angle of 60 degrees with the lines of centers of the two spheres. So basically, we'll get something like this, right? And this angle here is 60 degrees. Okay, as we've already mentioned here, it's moving with this speed here. So 10 meters per second. Okay. And if you really want to here, you can also include the horizontal component. You don't need to. If we do, I'll do that in a different color. So for the horizontal component here, that would just simply be 10, the magnitude of the speed here. Well, the velocity, obviously the speed is just the magnitude anyway. So 10 cos 60 degrees. Okay. And that there is the horizontal component for sphere A. In terms of sphere B here, well, it's stationary, right? So the horizontal component here is just 0. Okay, so we don't need to worry about that. I wouldn't even bother kind of drawing it on. We'll just leave it blank. Okay. So I think that's everything there for the before diagram. Let's just quickly draw then the after diagram here, which will be pretty similar, just slightly different, right? So after here. So for the after diagram, again, we'll have two spheres, just like we've got here. And again, I'll just quickly draw these. It won't be a masterpiece, but it doesn't really matter. Something like this again. This is A, this is B. Again, I've got my centers here and also my lines of centers. Something like this here will do. We've got the centers. Something like this, right? And what we've also got here is our horizontal components now, right? So B clearly won't be stationary anymore because it's been hit by A. So we have horizontal components here for both A and B. Now, we don't know what those are. So I'm just going to call the horizontal component for A here V. So it'll be V meters per second. And in a similar fashion here for B, I'll now call the horizontal component here for B W. We get W meters per second. Okay. And for A here, we do also need to account for the vertical component. So for the vertical component here, this would just simply be 10 sine 60 degrees. Okay. And I think at this point here, that gives us everything that we need then in terms of the diagram. So that's took us 5 minutes already, believe it or not, just to set up the diagrams. But it is an important step here for solving problems such as this one. Please don't be lazy and attempt this without a diagram. Honestly, I promise you it won't end nicely. Don't be lazy. Okay. So as I already mentioned then, what I'm going to do here is just let V and W be, so V and W here, sorry, will be the components of the velocities of A and B after the collision, and they act parallel to the line of centers, right? So V and W will be the components. So be the components here. Be the components of the velocities of the velocities of A and B. I won't bother mentioning or writing down here that they act parallel to the lines of centers here. Hopefully that's just obvious anyway from the diagram. Okay, so that's the first point here. Now, as B is stationary before the impact, it will move along the line of centers after the impact, right? So once these two spheres here collide, then B will move along the lines of centers here, okay? Now, in that case, then we will have no change in the component of the velocity perpendicular to the lines of centers, right? So in that case, then what I've got here is 10 sine 60. That's this vertical component here. So 10 sine 60. Well, sine 60 then, the exact value of that is root 3 over 2. So what I've got here is 10 times root 3 over 2. 10 over 2 just gives us 5. What we get here then is 5 root 3, right? So this vertical component here is just simply 5 root 3. If you want to replace it here with 5 root 3, that's fine. But for now, just keep it as it is here. Okay. So where do we go from here? Well, what I can now consider here is the conservation of momentum along the lines of centers, right? So just make a note here. So conservation of momentum. So conservation of momentum. So conservation of momentum along, I'm just going to put along here, LOC, meaning the lines of centers here. And by the way, what I'm going to do here is take to the right as positive. So we're taking to the right as positive here. I think that makes sense given that we're taking everything to the right here anyway. So to the right, to the right, to the right. So clearly we'll just take to the right as positive. So in that case then, what do we get here? I'm going to get 10 cos 60 times by 3. So 3 times by 10 cos 60. Like so. And that is equal to, so the mass here won't change, right? So this mass here is also 3. So 3 times by V, that's positive because it's acting to the right. So 3V plus 2W. The mass here is 2. So 2 times W, we get 2W. Perfect. And what we've got here is a linear equation. So let's just simplify this here. So cos 60 is a half. So 10 times a half is 5. 3 times 5 is 15. So we get 3V plus 2W is equal to 15. And this here, we'll take this as equation 1, right? Because the hope here is that we can form a second linear equation. And once we've got 2 linear equations here, we can just solve those simultaneously, right? Just basic GCSE maths. So how do we form a second linear equation here? So at this point here, to form a second linear equation, we can just now use Newton's law of restitution, right? So now use Newton's law of restitution. Okay, hopefully I'm spelling this correctly. English is not my strong point. So now using Newton's law of restitution. So to make life easier here, don't forget then that E, the coefficient of restitution, is equal to V2 minus V1 all over. So all over then U1 minus U2 here. So to make my life easier as well, what I'll do here is just multiply through by U1 minus U2. So V2 minus V1 is equal to E, the coefficient of restitution, times U1 minus U2. You'll see why in a moment. It just makes life a lot easier here. So what is V2 and what is V1 here? So V2 here is W and V1 will just be V, right? So V2 is W minus V1, which is V. So I get W minus V is equal to them. So we have E here. So the coefficient of restitution, as we're told in the question here, is 1 over 2. I've got 1 over 2 times by them. U1 minus U2. So U1 here, what is that? So U1 here is going to simply be this component here, right? 10 cos 60 degrees. So U1 is just simply 10 cos 60 degrees. There is no U2 here because B is stationary, right? I'll get 1 over 2 times 10 cos 60 degrees. Perfect. So cos 60 degrees here again is a half. 10 times a half is 5. 1 over 2 times 5 gives me 5 over 2. Perfect. So what I get here then is our second linear equation. So W minus V is equal to 5 over 2. Perfect. Now, at this point here, if I call this equation 2, I now have 2 linear equations, right? And clearly, if we have 2 linear equations, we can just solve those simultaneously. Now, I'm not going to go into a massive amount of detail here as to how to solve, these simultaneous equations here, equation 1 and equation 2. That should hopefully be very straightforward. It's just basic GCSE maths. If I write them down together, you can see what I mean then. So equation 1 is 3V plus 2W is equal to 15. And then for equation 2 here, that's minus V. So minus V plus W is equal to 5 over 2 or 2.5, whichever you prefer. And basically, we just need to solve these simultaneous equations here. Now, clearly, I can just use my calculator here or just do it by hand. Either way, this should really be straightforward. But we should get them. So solving here, we find that v is equal to 2 and w is equal to 4.5. Perfect. Okay. So just be careful then, because we're not done here, right? Because what we actually want then is the magnitudes and the directions of the velocities of A and B immediately after the impact. But we're pretty close at this point, right? We've now found V, and we've also found W, right? So that's these horizontal components here for after the impact. So at this point here, the magnitudes of the velocities is just the speeds, right? So for the speed of A then, so speed of A, let's just do that over here. So the speed of A then, well, that's just going to simply be the square root here. So I now need to consider the components here for A, right? So this is for after the impact, by the way. So I get 10 sine 60 degrees squared. Now 10 sine 60 degrees, as we evaluate here, is just 5 root 3. I've got 5 root 3 squared. So 5 root 3 squared. Plus then v squared, but v is just 2, right? So plus 2 squared there. What does that give us then? So 5 root 3 squared is 75, 2 squared is 4. So 75 plus 4, we get root 79 here. Okay, so the speed of A here is just simply root 79 meters per second. So ms to the minus 1 here. For the speed of B then, so for the speed of B, well, this should hopefully be nice and straightforward, right? The speed of B here will just simply be the magnitude of whatever W is, and W here is 4.5. So clearly 4.5 squared, take the square root of that, you just get 4.5 anyway. So the speed of B here is 4.5 meters per second. Perfect. Okay. But we're not done here, because we also want the directions of the velocities. So as you can see then, these questions are a little bit tedious, but we're nearly there now, I promise. So how do we find the directions of the velocities here? So for sphere B then, that's pretty straightforward. Sphere B has this speed here along the line of centers, right? It's just traveling along the line of centers. So the speed of B is 4.5 meters per second along the line of centers. Along the line of centers. Perfect. What about A then? So with A here, it's not quite as straightforward. We actually need to apply a little bit of trigonometry here. So for A then, I'll do this in a different color here, just at the bottom. So for A here, what I need then is arctan, or tan inverse, whichever you prefer. That's right, this is arctan here, since I've already mentioned that anyway. So arctan of, so we take 5 root 3, that's this component here, right? 10 sine 60, so 5 root 3. So 5 root 3, and that's all over this component here, v, right? Which is just 2. So just put into your calculator then, arctan of 5 root 3 over 2. And if you do this correctly then, what you should get here to the nearest degree is 77 degrees. So in that case then, A is moving at 77 degrees. I can't speak. We're nearly there. A is moving at 77 degrees to the line of centers at this speed here. And the speed of B is 4.5 meters per second along the line of centers. So to quickly finish with here then, let me just quickly summarize all of that. I'm happy with this one here for B. So put a bubble around that. That's fine. I'm going to take that as my solution here. Good stuff. For A then, I've mentioned that here underneath then. I'll do that in a different color as well. I'll do that in, let's do it in blue. So A is moving at 77 degrees to the lines of centers. Lines, I should just put a S there as well, lines of centers. Doesn't really matter too much. I'm just being a little bit pedantic. Lines of centers. So A is moving at 77 degrees to the lines of centers here with a speed of, what was the speed here? Root 79 meters per second. Root 79 meters per second. And there we go. Thank goodness I hate this topic. There we go. That is the solution, right? So I kind of split this up into two different parts here. So this was for B. So the speed of B is 4.5 meters per second along the line of centers here. And then for A is moving at 77 degrees to the lines of centers with a speed of root 79 meters per second. There we go. So like you can see, and as I mentioned a little bit earlier on, these questions are not particularly easy. There is quite a lot of different things going on here. It's applying a lot of different things from Further Mechanics 1 overall. As you can see here, I've got conservation of momentum, Newton's law of restitution, everything that we kind of learned here for oblique impacts, right? So there is a lot going on, and hopefully this demonstration and this explanation here has helped. If you're not too sure about anything, as always, please just leave a comment and I will try my best to help. But there we go. I've had enough of this topic. And that brings us to the end then of this video here on oblique impact of smooth spheres.